If there is one subject that students absolutely fear when it comes to computer networking, it is the concept and the subject of TCP/IP subnetting. They are just so petrified about this because maybe they've watched some really poor explanations on it. Maybe they've seen some very, very difficult to understand mathematical explanations as to what's going on. Maybe they've just heard from their peers that it is very, very difficult to master. Well, here in our live lessons, have no fear, folks. We are going to first make sure you're completely aware of why we engage in subnetting our networks to begin with, and then we will break down this important topic, and we're going to make it very, very simple for you to do. So I hope you'll join us in this live lesson as we look at this critical and often feared subject of TCP/IP subnetting. It's time now for us to tackle a subject that strikes fear oftentimes in the heart of students, and there's no reason for that. What we're going to look at right now is TCP/IP subnetting. In the last lesson of this Network Plus Video Mentor series, we went ahead and we looked at that internet or network layer of the OSI or TCP/IP model, and we saw that there were IP addresses that were defined there, and these IP addresses would help us find a network machine, identify a network machine at that particular layer. Well, in this particular video, we're going to take a look at this concept of ipv4 subnetting, and we're going to see exactly, first of all, why we need to torture ourselves with this topic. Why do we need to do all this math? And by the way, if you're not into math, if it's not your thing, have no fear, because this math is going to be very, very elementary in nature, as you'll see. But here's the deal. We really need to learn this because when it comes to putting workstations on a network together, the designers warned us. They said, look, when you get up to about 500 workstations all on the same network with each other, you're going to get into a real problem thanks to the amount of potential broadcast traffic that could result. So in actual network implementations, we tend to not even get close to that number of 500 these days. So when we have a network address, we want to go ahead and break that network IP address up into smaller network IP address segments so that we can create what we call subnets, or oftentimes we'll just call them subnetworks. And we can put routers in between these subnetworks and break down the network into smaller chunks. In order to subnet, we have to understand these powers of 2. This is how the binary works inside one of those octets that we discussed in a previous lesson here. So the powers of 2 work like this, and you probably learned this long, long ago in your math class. We have 2 to the 0 power equals 1, and then we just double it. 2 to the 1 equals 2, 2 to the 2 equals 4, 2 to the 3 equals 8, all the way up to 128 with our 2 to the 7. I want you to notice here the only one we really have to memorize, and you probably memorized this already, that anything to the 0 power equals 1. That's right, anything to the 0 power equals 1. If you can remember that, and then just double it, 1 to 2 to 4 to 8 to 16, then you've got this powers of 2 thing mastered. So this is the first bit of information that we need to commit to memory, and as you can see, it's really not that bad at all. Now, one of the interesting skills that we have to be able to do here is to do decimal to binary conversions, potentially, as we're starting out in this networking world, or binary to decimal conversions. This is very, very simple. And in certification exam environments, for instance, you're going to build this table that you can see I've built for us on screen. And it's amazing. This table is all that you're going to need in order to solve any of these types of questions on subnetting or binary arithmetic for these network layer devices. Let me repeat that. I know it's surprising to you, but it's the truth. This table is all you need. 2 to the 7th over there on the far left, all the way to 2 to the 0 above my head here. That's the 1 value, and we just want to practice building this chart because it is all that we are going to need. Trust me, folks. Let's go ahead and take a look at an example here with this decimal to binary conversion. So if I have a number, watch how easy this is to do, and you're going to love practicing this. If I have a number, let's say that number is, oh, and you can just totally make up anything. Let's say I have the number 87. Okay, so let me get my drawing tool out here. We have the number 87. Okay, now what you do to convert, oh, wait a minute. The title of this slide is binary to decimal conversion. Okay, so, oh, wait a minute. Okay, decimal to binary. There we go. So we're going to do our decimal to binary. So I was right. We're going to go 87 as an example of some decimal number. Now we need to be able to convert that into the binary that we saw actually makes up our IP addresses. Here's how easy it is to do, folks. It's all about subtraction. All we do is we say, can we take 128 from 87? And the answer is no, we can't. So we know there's a 0 in that bit position. Can we take 64 from 87? The answer is yes, so we place a 1 in that particular bit position, and then we subtract our 64 from 87. We get 3 and 2. So now we have a leftover of 23. I told you this was easy math. Can we subtract 32 from 23? No, we can't. So no subtraction to do there. Can we subtract 16? Yes, we can. So we put a 1 in that position, and we subtract our 16. Ooh, this is a tough one. Subtract from there, and then 7. The remainder is now 7. Can we take 8 from 7? No, we can't. Can we take 4 from 7? Yes, we can. That's a remainder of 3, so we have a 1 and a 1. Look at that. So 87 in binary is 0, 1, 0, 1, 0, 1, 1, 1. Let's circle it here. There is the binary for 87. So in a octet of a computer, when the computer sees 87, the computer is seeing it as 0, 1, 0, 1, 0, 1, 1, 1. It is that simple, folks. Now, I'm sure you're like me. You always want to check your work, right? We're always going to want to check our work. So one of the things you can do when you're practicing is you can go ahead and you can bring up the Windows calculator because it has a scientific, or even cooler, a programmer's view. And what we can do is we can say decimal 87, and then we can say we want to see that in binary, and it tells us that we were right. It's 0, 1, 0, 1, 0, 1, 1, 1. Just what we said in our example. Notice they trim off the leading 0 when they do this, okay? When the calculator does it, it trims off the leading 0. In fact, if you look right here, you can actually see it. They show you the binary in here in this programmer's view. And there it is, 0, 1, 0, 1, 0, 1, 1, 1. Hey, I pulled that 87 example right off the top of my head. It's got a nice ring to it, doesn't it? By the way, this particular skill, converting from decimal to binary, is something that you're going to have to practice with in order to be able to do very quickly and efficiently. So practice with this, okay? And you may want to watch portions of this video over again. This is definitely a video you might be watching over again until you have all of this down. Don't be surprised if you're in that boat. Many of us were when we learned these skills. You got to watch the video a couple times, practice it over and over again, and notice you can pull out numbers right out of your head. Now, I've got great news for you. Going from binary to decimal is even easier. Much easier, folks. Watch this, because all we're doing here is addition. Let's say we have the binary number. The binary number we have is, let's say, 0, 0, 1, 0, 1, 1, 1, 0. So we are given that binary number, and we are asked to go ahead and convert that to decimal. It is easy. We've got 32 plus 8 plus 4 plus 2. It is a simple process of adding up those values. 32 plus 8 is 40, plus 4 is 44, plus 2 is 46. So this number to me looks like 46. We can go back over to our calculator in order to check our work. I already forget the numbers I spit out there, but you can check your work. 46, and then we can convert to binary. You get the idea. So, very, very easy, these exercises of decimal to binary or binary to decimal. Very cool. Once we have this mastered, we realize that the subnet mask is the actual structure that is going to tell us how many of the bits identify the network and how many of the bits identify the host. We already talked about this a little bit earlier, didn't we? When we were saying that an IP address is hierarchical. A portion of it identifies the network, and a portion of it identifies a host on that network. So think about this. When you look at your computer's configuration for an IP address with our command prompt and our ipconfig, we know we always get a subnet mask that's reported. Yeah, the subnet mask is a necessary ingredient because the subnet mask is that accompanying piece of information that determines how big is your network portion and how big is your host portion of the address. Pretty cool. That's the job of the subnet mask. Remember when we had our Class A, Class B, and Class C networks, with there being a network, host, host, host in Class A, and Class C, for instance, network, 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 host? Well, notice that the subnet masks for these default classes kind of follow that logic. The default mask for the Class A is all ones in the first octet of the subnet mask, thus 255000. For a Class B, it's 255.255.0.0.0. Sure enough, the network bits and the host bits. And then for the Class C, it's network, 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 host. So it's 255.255.255.0. Notice how the continuous ones, all the ones in those subnet masks go right in a row, and they mask off what is the network portion. Yeah, that's why it was named a subnet mask. It's masking off which portion of the 32 bits identifies a network. When we subnet, folks, and here in the Network Plus Video Mentor series, we're going to keep it simple. We're going to keep it focused on Class C addresses. When we subnet, what we're going to do is we're going to take the mask of 255.255.255, and we're going to extend it. We're going to extend the mask into this fourth octet. And when we do that, when we extend the mask into that fourth octet, the additional bits that we use for additional network addressing, those are our subnet bits. Those bits that we borrow or steal from this fourth octet, they're going to allow us to create these additional subnets. Pretty darn cool. Okay, so let's go ahead and see something now. What would be the possible values that we put in that fourth octet? Well, we always have to steal or borrow or use these bits in a continuous pattern. So we could steal 1 and we could have way over there a 128 value in that fourth octet. We could steal 2 and get a 192. We could steal the first 3 and get a 224. You get the idea. These values here are what's possible for our fourth position there in our class C's subnet mask when we borrow the bits. It's going to be 0 or 128 or 192 or 224 or 240, 248, 252. And we know why now because we can do the conversion. We know that this is just how the conversion would work based on the conversions that we saw earlier. Pretty cool. Now, there's something that you really need to realize about this subnetting, and that is you're going to play a little balancing act. And you need to decide how many subnets you need, and then you need to figure out how many hosts will be available in those subnets. And this is a balancing act. Watch this. The number of bits you steal, n in our little formula here, that dictates how many subnets you can create. And it's 2 raised to the n, the number of bits you steal. So if we steal 4 bits, how many networks can we create? 2 raised to the 4. And look, the answer is in our chart that we wrote on our scratch paper. How cool. It's 16. We can create 16 networks. Let's do another one. If we steal 5 bits, how many networks can we create? 2 to the n, 32 networks can be created. Pretty cool, huh? Now, how many hosts can live in each of those networks? Well, you look at the bits that are left over. In our Class C example, if we steal 5 bits, okay, we can create 32 networks. How many bits are left over? If we steal 5 of the bits, 3 of the bits are left over for hosts. Plug that into the 2 to the h minus 2 formula, and that's how many hosts you can have. 2 raised to the 3 is 8, minus 2 is 6. Wow. So if we steal 5 bits, we can create 32 different subnets, but each of those subnets can only have 6 workstations. Let's say that's not going to work for us. Okay, well, why don't we steal only 3 bits? Perfect. 2 raised to the 3, we can create 8 networks. There'll be 5 bits left over for hosts. Now we can have 8 networks, and each of those networks can have 30 host workstations on that particular subnet. Folks, these formulas are often called the magic formulas. They are magical for us in this exercise. They tell us how many different networks we're going to be able to create, and the second formula with the leftover host bits tells us how many devices can live on each of those networks. So now we get to the ultimate example of this, and again, you'll probably want to watch this a few times. Questions that would involve subnetting. And here is a classic one for us to look at. On what network does 192.168.5.139/27 reside? Notice the /27 here. This is what's called prefix notation. It's a shorthand notation on representing the subnet mask. Instead of going 255, 255, 255, whatever, they're just doing /27. The number of bits that are on in a row in the subnet mask. Very interesting. All right, so let's think about this. We want to look at this last octet and what is going on with the binary. All right, first of all, by the way, we're going to break this down into binary, and then we are going to give you a shortcut so you don't have to go through all this work. But before we get into the shortcut, I want you to see how this would work in binary. All right, if we go ahead and we take that fourth octet of 139, okay, so we're going to go ahead and focus on that third octet. Okay, folks? And let me get my handy dandy drawing tool here. Where is my drawing tool? Where did it go? Okay. Here we go. All right, if we take this third octet, oh, wait a minute. Struggling with my drawing tool, and we absolutely want to draw here, right? Okay. Trust me, we do. All right, here we go. So we take this third octet of 139 and we convert it into binary, okay? Now just trust me, we are going to do this just quickly because you already know how to do it, okay? So just trust me that it's right. Here's what we get. 1, 0, 0, 0, and then we have 1, 0, 1, 1. Okay, a little trust me moment here. Just, I'm telling you that's right. Okay, so that's 139 converted into our binary. Now look at the subnet mask. There's 24 bits for the 255, 255, 255, the default, and then there's 3 bits more, isn't there? We stole 3 bits for the subnetting. Now, if we just fill these in with zeros, because that's what the subnet mask would have in those positions. Okay, so this is pretty cool. Here's our IP address, of course. And this is our subnet mask in binary. All right, so look at this. I'm going to draw a line here because this represents our subnetting, right? And this over here represents our hosts. By the way, in this example, you can already see that we have a situation where we can create 2 raised to the 3, 8 networks, and each of those networks can have 30 workstations. Pretty cool. So we apply those magic formulas to this particular scenario. Now, this question says, on what network does 192.168.5.139 reside? What network does this particular host reside on? Well, we can figure this out with this neat ANDing process. 1 times 1 in this first bit position here is 1. 1 times 0 is 0. 1 times 0 is 0. 0 times 0 is 0. 1 times 0 is 0. 0, 0. You get the idea. 0. And this right here, folks, after you get done ANDing, this is the network we reside on. Okay. Take this and convert it back to decimal, and we have our answer, don't we? 192.168.5.139/27 lives on the 192.168.5.128 network. Wow. How cool. Now, I told you I will show you a shortcut instead of all this a little later on. But like I said, I wanted you to see that longhand version of figuring out that the answer there is 128. I wanted you to see how that works so you can see how it works, okay, how the computer does it. Okay, so now we could ask the question, what's the first and last usable host addresses on that particular segment, on that particular network that we just looked at? Well, guess what? That could be done by analyzing the binary. Once again, we have that IP address converted to binary of 1, 0, 0, 0, 1, 0, 1, 1. We have our subnet mask where we're borrowing the 3 bits. And then we divide them, and we know the network is 1, 0, 0 that we're looking at here. And then the first usable host address would be 0, 0, 0, 0, 1, right? Pretty cool. The last usable host address would be 1, 0, 0 for the network, and it would be 1, 1, 1, 1, 0. Wow. This comes out to 129 is the first usable host address, and 158 is the last usable host address. Now again, that's a lot of work, isn't it? That's kind of a lot of work. I mean, well, it's not that much work, but I'm going to show you how to calculate this even faster. By the way, the last question that could be asked here is, what is the broadcast address? And that's when we have all ones in these host bits. So the broadcast address would be 1, 0, 0, 1, 1, 1, 1, 1. And you work that out as far as converting it to decimal, and it's 159 is the broadcast address for that particular network. Are you ready for the magic shortcut? I am. I love shortcuts, but I only love shortcuts once I have figured out how it works. It's like, I like to learn how to change my own oil in the automobile. And then after doing it a few times, I'm like, boy, I know exactly how that works. I'm going to go to a trusted mechanic and I'm going to look over his shoulder as he does it. That was a dumb analogy. In fact, it was such a bad analogy because I don't know how to change my own oil. All right, here's the shortcut that always works here. It's so cool. How many bits deep did we go into that particular subnet mask? Or how many bits did we steal? We said we stole 1, 2, 3 bits. And we could tell that, of course, from the /27. We stole those 3 bits. Well, what you do is you go in 3 bits deep into this chart and see this number 32? That's 30. That 32 is how our subnets increment. Yeah, it's how our subnets are going to increment. It always works. How many bits you steal, you go that deep into your conversion chart, and it always works. So our subnets are 0 to 31, 32 to 63. Whoops, put the 3 in the wrong place there. To 63, and then 64 up to 95, 96 up to 127, and then 128 up to 159. Unbelievable. That trick always works. So here we look at 139 and we figure out, you fall right in there. You live on the 128 network. And what's the first usable address? It's 129. It's one more. What's the last usable address? It's 158. And what is the broadcast? It's 159. Amazing. And this shortcut always works. So folks, this is the joys of subnetting. And you're going to want to practice this, as I said. You can practice this by using great tools that are available free of charge for you on the internet. Check this out. We go up to the internet and we go to Subnet Calculator, for example. You got to spell it right. Spelling counts. Calculator. And the very first link is one of my favorites. The very first link is Online IP Subnet Calculator, and here it is. We can go 192.168.5, whatever number we had. What do we have in that example? I think we had like 139. And then you can say the /27. And look, it calculates everything for you, and you can check your work. How cool is that? It's very cool. It's an easy way to check your work as you're practicing with this. Watch this. Let's go over here, create a third tab, and I'm going to do a search on subnet practice. Very first link that comes up is IP subnet practice. It's from San Bernardino Valley College. Thanks to those great folks. They created this cool practice. You say 192.168.5. What do we have? 139/27. And then you work it out on paper, and then you go ahead and, okay, given that address, let's see. Oh, then you guess. Okay, I think that lives on 192. You don't guess, you work it out. 168.5.128, and then you say check. And it says, nope, you're wrong. You're wrong. So what did I do wrong here? 192.168.5.139. And, oh, you know what? You can't put your own values in here. That's right. What you do is you go, new problem. There you go. And they give you one. And then you work it out. Whew, that scared me for a minute. It was like, wow, did we do it wrong somehow? So that's what you do. You say new problem. Now, what I recommend you do, folks, is we want to focus on Class C addresses. So you're going to use those Class Cs. So just keep clicking new problem and make sure it's giving you a Class C in order to practice with. All right, pretty cool. If there's one thing I could change on this, it would be to tell it, look, we want Class Cs only, for instance, but you get the idea. Hey, it's a free tool, so we can't complain that much, can we? Well, folks, thank you so much for attending this particular Video Mentor edition. And we will see you in the next video. I bet you, if I'm thinking about this logically, I bet you now we're ready to start getting on switches and routers and seeing how these network devices work. And we'll be plugging in these IP addresses and seeing how they get involved. So again, thanks so much for joining me, everyone. Really look forward to seeing you in the next video here in our Video Mentor series on Network Plus.